Hello, students. We are here to discuss some common continuous distributions. This list does not contain every possible continuous distribution. It also doesn't contain all the continuous distributions we will use this semester. However, it's a very nice introduction, and we will see a few continuous distributions right now. So the first one you might have seen before, standard normal distribution. We will typically use capital Z for a random variable following this distribution. Well, the thing we can point out right away is the support for the standard normal. Really, the support for any normal distribution is minus infinity to infinity. Moreover, here is the probability density function. This is this beautiful bell-shaped curve that we see graphed here. Now, the mean is 0 and variance is 1. Equivalently, the standard deviation is 1. Now, there's some beautiful things to point out about this probability density function. Let's do this in orange. You notice, so what have I done here? My vertical lines, here's the mean, and here's the mean plus 1 standard deviation. And here at x equals 2 is the mean plus 2 standard deviations. At x equals minus 1, it's the mean minus 1 standard deviation. And this vertical line I have included in my picture is the mean minus 2 standard deviations. What else can I point out about this picture? Well, if you stare right here, you see we have a maximum at x equals the mean. Moreover, this is a line of symmetry. So you notice this graph of the probability density function is symmetric about the line x equals mu. Now, the final thing I will remark about regarding the graph of this probability density function is what's happening at mu plus sigma and mu minus sigma. We have inflection points at x equals mu plus sigma and x equals mu minus sigma. And I will draw a line to them on my graph. Here's one, and there's the other. So all of this is important shape information regarding this standard normal distribution. Okay, let's move on and talk about a general normal distribution. Well, here's the amazing thing. Let's suppose we start out with Z is distributed as n of 0, 1. So standard normal distribution. Take any mean mu, take any standard deviation sigma, and what we're going to do is perform this linear transformation. Now, generally, if you take a linear transformation of a random variable distributed some way, the linear transformation will not have the same distribution. We saw that in the last video. But the beautiful thing is, for the normal distribution, this is normally distributed, meaning, well, bell-shaped curve. And we can calculate, let's see, the expected value of x using the formulas we discussed in the last module. This would be mu plus sigma times the expected value of z. Expected value of z is 0, so we just get mu. And similarly, the variance of x would be sigma squared times the variance of z. The variance of z is 1, so we get sigma squared. So you see, by performing this linear transformation, we have a normal random variable with this mean and this standard deviation. And typically, we will write x is distributed as normal, where the mean is mu and the standard deviation is sigma, like this. Now, the PDF, well, oh my goodness, this is quite intricate. It's even more intricate looking than when we had mean 0 and standard deviation 1. Now, the good news, as intricate as this formula looks, we do not need to memorize it or be able to calculate it with it by hand. So R has this distribution. I'll just even say this probability density function pre-programmed. So this is built into R. I mean, similarly, the cumulative distribution is pre-programmed, but I'll just mention this at the moment. So I'm not so concerned about this formula for the purposes of this class. What I'm more concerned with is understanding the shape of the probability density function. And here we're looking at it. So here I have a specific example. I let X be the IQ of a randomly selected American, and then X is distributed as, well, normal distribution, mean is 100, standard deviation is 16. Doesn't this graph look familiar? Why, yes, it does. So this is another bell-shaped curve. In fact, all I need to do is go back to this bell-shaped curve, which was n of 0, 1, copy and paste. Well, in everything I said about the last bell-shaped curve, which corresponded to n of 0, 1, remains true. Namely, the PDF has a maximum at x equals mu. We have a line of symmetry right here. Inflection points at x is mu plus sigma and mu minus sigma. For instance, now, this height, of course, is not going to be the same as this height because the total area from minus infinity to infinity under the curve has to be 1, but the general shape, bell shape, remains the same, really for all of the normal distributions. All right. Now I want to discuss the gamma family of distributions. The thing is, sometimes your data may not be so beautifully bell-shaped, and the normal distribution may not be the best model for your data. And so there are other continuous distributions. And one entire family I will talk about is the gamma distribution. Now, generally, we have two parameters, alpha and beta. They both need to be positive. Alpha is referred to as the shape parameter, beta referred to as the scale parameter. Let me just say right now, my notation of alpha and beta is to match our texts. Some other textbooks or other probability resources might use different letters than alpha beta, but it is always the case that we have a shape parameter and a scale parameter in our gamma distribution. So I'm going to start with a special case where the scale parameter is 1. Sometimes texts will call this the basic gamma distribution. For instance, maybe before I say anything else, all of these in the gamma family have support 0 to infinity, so positive real numbers. And we can see that here. Probability density function for this basic gamma distribution, well, it's also quite intricate looking. We have 1 over gamma of alpha, x to the alpha minus 1, e to the minus x. And this capital gamma is what's called the gamma function. It itself is this improper integral. Okay, well, I'm just going to tell you the good news once again is that R has this PDF pre-programmed. So memorizing formulas for probability density functions, you really don't have to do. That's the good news. But what I want to kind of look at is, here's 3 graphs. My scale parameter is 1 throughout. Shape 1, shape 2, and shape 7. And I made these in R. What you'll notice, what changes is things like increasing, decreasing, concave up and down. Fundamentally, the shapes are different. This one is decreasing throughout. This one, you notice it's concave down, and then it's concave up. This one is concave up, then concave down, then concave up again. So the shape fundamentally is different as you vary this shape parameter. But also, as you look at these 3, you notice none of these are bell-shaped. None of these are symmetric, like we see in this beautiful bell curve for the normal distribution. Okay, now, when you have this shape alpha, this is this basic gamma distribution, the mean is alpha, and the variance is also alpha. Very nice. Let's discuss the general gamma random variable. Well, we just take beta times x, where x is a gamma random variable with shape alpha and scale beta equals 1. Here, beta is some positive number. So here, this gamma random variable has shape alpha and scale beta. Well, we can calculate the mean and variance just because this random variable is a linear transformation of this basic gamma random variable. So the mean, well, this will be beta times the expected value of x, which is beta alpha. And the variance will be beta squared times the variance of x, which is beta squared alpha. So here I have 3 graphs. They all have the exact same shape parameter, alpha equals 3. And then I've changed the scale, 1/2, 2, and 8. And you can see what happens. So fundamentally, the shape is the same, but the scaling affects the x-axis. Now, I'll mention 2 special cases of the gamma distribution. These have their own names. These come up quite often in biology and bioinformatics. In fact, generally, the gamma distributions often model wait times, for example. All of these, because they are gamma distributions, the support is positive real numbers. Now, the exponential distribution. Well, what makes it an exponential distribution is it's a gamma distribution that has shape 1. But typically, instead of using scale beta, we will use what's called a rate parameter, which is 1 over beta. Or another way to say that is that beta is 1 over lambda, and lambda is called the rate parameter. So the mean here, well, we know the formulas for the gamma distribution. So the mean is alpha beta, which is 1 times 1 over lambda. This is 1 over lambda. And the variance is alpha times beta squared, which is 1 over lambda squared. So this is the mean and variance for the exponential distribution. Now, just as a remark, the probability density function is here, lambda e to the minus lambda x. I'm going to do an example where I actually work with this. It's one of the few probability density functions for a named distribution that we can actually integrate by hand. So I'll do an example with this on the very next page. Okay, chi-square distribution. The shape is always of the form k over 2, where k is called the degrees of freedom, and the scale is beta equals 2. So here, once again, we can calculate the mean and variance. This would be alpha times beta. We just get k, this degrees of freedom, and the variance is alpha times beta squared. This is 2k. We will use chi-square distribution later this semester. Well, I've just graphed one example of an exponential distribution, one example of a chi-square distribution. Here the rate is 1 over 5, and chi-square has 8 degrees of freedom, and we can see these probability density functions. Okay, this is the only example in which I'm going to do some calculating of probabilities. So as I mentioned, I'm going to do this by hand. In fact, let's write out the probability density function. What I have graphed here is lambda e to the minus lambda times x. So this is my probability density function. I'm going to use fundamental theorem of calculus and integrate these functions by hand. You could also use R to integrate this probability density function. Moreover, I will also mention how you could use R with the pre-programmed functions. In fact, I might show you that after we do this by hand. Okay, the first one Now, I'm doing this in part to stress, how do you calculate a probability for a continuous random variable? Well, area. So what is the probability that x is bigger than 3? Well, 3 is probably here. The probability that x is bigger than 3 will be this area. This area is what we're looking for here. So how can we calculate this? Well, one way would be you could integrate from 3 to infinity of the probability density function. This would be 1/2 e to the minus x over 2 dx. This is an improper integral. Now, we also know the total area under the curve is 1, so you could take 1 minus and then just subtract off this part, which is the integral from 0 to 3. The integral from 0 to 3. So I think I'll do it this way, so I don't have to worry about an improper integral, but then I'll also mention how we could use a cumulative distribution function. All right, so when I integrate 1/2 e to the minus x over 2, I get minus e to the minus x over 2, and then I can evaluate between 0 and 3. This will be 1 minus, well, evaluate at the upper limit of integration, and then minus a minus becomes a plus, and then the lower limit of integration. Now, 1 minus 1, e to the 0 is 1. That's 0, so we just get e to the negative 3 over 2. This is approximately 0.2231. All right, so we have answered this first one. And as I mentioned, if you didn't want to integrate by hand, we can integrate numerically using R. Let's make an important note here, and I'm going to do this right after I finish this. My important note. How else could we calculate this? Well, we can calculate 1 minus capital F of 3, where this is our cumulative distribution function. So capital F of x is the probability that x is less than or equal to x. This is the cumulative distribution function. This gives us another way to calculate. And in particular, this is a very short line in R, which I will do in just a moment. Okay, next one. We want the probability that x is bigger than or equal to 1 and less than or equal to 4. Let's shade this in my graph. So 1 is about here, and then we have 4. This is the area we are looking for that I have shaded. It's the area under the curve between x equals 1 and x equals 4. Gives us the probability here. So we could integrate 1 to 4 of my probability density function. This is 1/2 e to the minus x over 2 dx. Well, we have the antiderivative for this above, or we could think about it again. We have minus e to the minus x over 2, and then we evaluate between 1 and 4. So this is minus e to the minus 2 plus e to the minus 1/2. This is approximately 0.4712. As I did in number 1, let me make my important note, and then we're going to look at R for a few moments. How else could we calculate this? In particular, how could we calculate it using the cumulative distribution function? Well, we could take here the probability that x is less than or equal to 4. This would give me all of this, but also down to here. And that's a little bit too much. So then subtract off this part. So minus like this, where I will just write it this way this time. Capital F of X is the cumulative distribution function. It's very important to understand why this works for the continuous distribution. So in a continuous distribution, there is no difference between less than or equal to in a continuous distribution because probabilities are areas. And so whether you put a less than or less than or equal to, either is okay for a continuous distribution, continuous random variable. Really, it's because in the continuous world, the probability that capital X equals any specific value is 0. As we saw in the last video, we must pay attention to the difference between those two in a discrete random variable. But here I don't have to worry about that. Okay, so we have calculated this just by integrating by hand. We've talked about how to calculate it using the cumulative distribution function. And so to close this video, let's spend just a few moments in R. If you are interested in learning about the R functions for the exponential distribution, you can enter, say, $PX. The P stands for cumulative distribution function. We discussed this some in the last video. Now, let's get started. In the first question, we calculated using an integral, but I also mentioned we could take 1 minus capital F of 3, and we're working with the rate parameter 1/2. So here is how I would enter this: 1 minus PX. There's the 3, and the rate is 1/2. And you see, we get 0.2231. And, well, that's the same thing I got integrating by hand using fundamental theorem of calculus. The second part, I remarked that we could take capital F of 4 minus capital F of 1, same rate parameter, and cumulative distribution has the prefix P. And so the line would be here. We take PX4 minus PX1. We have 0.4711954, and you can see this matches the answer we got by integrating. So this is all I'm going to discuss in this video. Thank you so much, class.